Welcome to STEM Professionals. In this video, we will discuss the problems and conceptual exercises of Chapter 2 from the book James S. Walker. So let's start with the video. So here in this question, we are given that a hot air balloon has lifted off and is rising at a constant rate of 2 meters per second. Now suddenly a passenger realizes that she left her camera on the ground. So her friend picks the camera and tosses it straight upward with the initial speed of 13 meters per second. Now when the camera is tossed, the passenger is 2.5 meters above her friend. And we have to tell how high the passenger is when the camera reaches to her. So this is the question. Now let me show everything on the figure. So we'll be taking this direction to be our positive direction, and this is the initial position for the camera. Now the hot air balloon is rising at a constant rate of 2 meters per second. So every time the velocity with which it is rising, it is 2 meters per second. This is the initial velocity, and this is the velocity at all the time. Now next, the initial velocity for the camera. So I will be writing initial velocity for camera. This is equals to 13 meters per second. Now when the camera was tossed, the hot air balloon is already traveled a distance of 2.5 meters. So this distance is 2.5 meters. Now suppose this camera reaches to her friend at this position. Suppose at this position. So we have to calculate this position, this x we need to calculate. Now, so I'll be using this equation because the acceleration is constant for the camera, and here the acceleration is 0. It is moving at a constant velocity. So in both the cases, we can use this equation, which is x is equals to x naught plus v naught t plus half at square, where this x is the final position, x naught is the initial position, v naught is the initial velocity, t is the time at a given position. Okay, and a is acceleration. So I'll be writing this. I will using this equation for camera first. So I'm writing for camera here. So the final position of camera, so let it be represented with xc, is equals to, now initial position of the camera, so x naught c, initial velocity for camera v naught c times t plus 1 over 2. Now acceleration, when this camera is tossed in the upward direction, it is under free fall. So acceleration would be in the downward direction, and since we have taken this direction to be positive, so a would be equals to minus g in this case. So I'll be writing in this minus here, and g times t square. Now again I'm going to use this equation for the hot air balloon. So we can write this is xb, the final position of balloon, is equals to x naught b, the initial position for balloon, plus v naught b times t plus half at square. So 1 over 2 a t square. Now since the balloon is moving with a constant velocity 2 meters per second, so acceleration for balloon would be 0. So this whole term would be 0. Now when the camera reaches to the passenger, so the final position for the camera and the final position for the balloon would be same. So we can equate these two equations. That is, I'm just writing it here. This is xc should be equals to xb. This is what we can write. So let's equate these two equations. So x naught c, the initial position for camera. Now initial position for camera is 0. So we can write it as 0 as it is. So 0 plus v naught c as it is multiplied with t minus 1 over 2 g t square is equals to, now this is x naught b, so x naught b plus v naught t, that's it. Now we can take these two terms to the right side. So x naught b plus v naught, this is v naught b. So v naught b multiplied with t. Now this term to the right side, so minus v naught c times t. Now we can take t common from here, so we can write this way also. minus this would become positive here when it comes to the right, so 1 over 2 gt square, and this is equals to 0. Now we're going to put all the values. So the initial position for the balloon, this is the initial position for balloon, which is 2.5 meter. So 2.5 meter plus the initial velocity of balloon, which is 2 meter per second. So this would be 2 meter per second minus we not see for the camera it is 13, so minus 13 meter per second multiplied with t plus 1 over 2 g. The value of g we have 9.81 meter per second squared multiplied with t square. Now 2 minus 13 is minus 11, so this would become minus 11 meter per second times t, and this thing we can take it a little bit here. Now this equation is a quadratic equation, so we can use like, let me first write the general form of the quadratic equation. This is equals to, now this would become 4.9, so 4.9 t square minus this is 11t plus 2.5. Now if you compare this equation with this one, ax square plus bx plus c is equals to 0. So this is it is in the form of quadratic equation. So the solution for this equation is given by the formula x is equals to minus b plus minus under root b square minus 4ac divided by 2a. This is the formula, and in our case we have the value of a to be 4.9, the value of b we have minus 11, and the value of c we have 2.5. So we can put all these value here. So in this case it will be t will be equals to minus of minus 11 plus minus under root b square is minus 11 whole square minus 4 times a is 4.9 multiplied with c is 2.5 divided by 2 times a is 4.9. So from here we'll get the value of t. We'll get two values. First one is 0.2 seconds and the next one is t equals to 2 seconds. So we have obtained two values for time, that is 0.26 seconds and 2 seconds. So let's see what all is happening here, at what time the camera reaches to the passenger. So when this camera is thrown in the upward direction, in just 0.26 seconds the passenger can catch the camera, but suppose he misses, he is not able to catch it, but the camera would still be moving in the upward direction with some velocity. It will reach to the maximum height where the velocity becomes 0, and again it will come back, and this balloon is still it is moving with some velocity, with this velocity 2 meter per second. Now when it comes back again, the passenger have a chance to catch the camera, and at this instant the time is 2 seconds, and at this instant the time was 0.26 seconds. So this is what is all happening. Both the time is correct. This is the time when the camera is moving in the upward direction, and this is the time when the camera was moving down. So we have calculated the time at which the camera reaches to her, but we need to find that how high is she when the camera reaches to her. So this distance we need to calculate, this distance. So for that we can use this equation for the balloon. Let me write the equation again. This is xb is equals to xb naught plus v naught t plus, now at square no need to write, this half at square no need to write because the acceleration for balloon is 0. So we can use this equation. Now its initial position we know it is 2.5 meter for the balloon, plus the velocity for the balloon is 2 meter per second, and time, now we can take either this time or this time, both will be correct. So I'll be taking this time, when the first time she have the chance to catch the camera. So this is multiplied with 0.26 seconds. So that would be equals to 3 meter. So this would be the final answer for this question.